Hello and welcome. Today is Tuesday, April 21st, and I have a few updates, and then we'll get going with our review number 3. So the update is the update to the school schedule here on out till the end of May, and then we have finals week in June, just 1 week before the virtual graduation ceremonies. um, and that is that Wednesdays will be teacher meeting days apparently, so no streams on Wednesdays. And so school will be a four day per week. Monday, only Monday, Tuesday, Thursday, and Friday. Yeah. Uh, your English teacher streams at the exact same time as this stream. Interesting. Streams, like how do they do it with like Microsoft, like Zoom? I don't think we're supposed to be using Zoom. Zoom got banned due to privacy concerns. I see. Yeah, even Google Google banned Zoom, and they don't. Google does not let their employees use Zoom. Yeah, that was true. You had to give up your privacy after 9/11. It's the price you had to pay. At least that's what they say. All right. So no streams on Wednesdays. Only 4 days a week. You know that you have your My AP assignment. The first one is due tonight midnight for E&M, and then next week, 1 week from today, you have your mechanics due. So make sure you work on My AP homework. Whatever it takes to force people to do their work. So if Sword Hero needs me to grade his work, then I'll do it. If that's the only way he's gonna get work done. If he, whoever needs a babysitter, I'll babysit. uh, hmm. Well, I certainly don't want people to just guess C and get it done with, right? So, so yeah. So we better do well. Right. Well, I mean, not everyone's name is going to be on my wall, and I'm not going to remember everyone, right? Oof. Some will be forgotten in the history books, never written about. Yeah, that's how it works, man. If you want to leave your legacy behind. Uh, well, you turned it in late, so you might get late credit. Might. Um, Ooh, Nobel Prize in physics. What are you gonna work on, Nishek? New gravitational waves? Did you see the new model? There's a new model of a big black hole and a small black hole merger. It's really cool. Typically, up to this point, the gravitational waves have only observed, similarly sized fusions. Uh, as far, a lot of them are just neutron stars. Now, neutron stars are pretty dense, so they're almost like miniature black holes, but not quite. But here we have, it was stated that one of them is somewhere around uh, 8 solar masses, 8 mass of the sun, whereas the other one's like 30 to 40-ish. Let's just say 30-ish. Um, and then as it started to spiral inwards and fuse, it started making waves that are the waves themselves were oscillating from side to side, and so you get some really cool things. And then eventually it spirals in, and then bloop, it disappears, and then the fluctuations in the space-time fabric also disappears, and everything goes back to equilibrium as and based on the collision during the fusion process, um, the new black hole will just have whatever momentum it had, and it'll just carry on whichever way it was going, due to conservation of momentum as well as conservation of angular momentum. Uh, well, I mean, if what was it? I'm sorry, man. You're the only one who couldn't get it turned in. So if everyone else did it, then it is what it is. It is what it is. There was no what assign. Wait, that's Big Doe. Huh? Big Doe? New prodigy confirmed. Who? Nishank? Yeah, getting a Nobel Prize as an undergraduate would be pretty big. Pretty big. All right. Well, Nishank, maybe you can do some modeling for fusion of various sizes of black holes, and I don't know. I don't know what else is up there. I mean, of course you can try opening up your own wormhole. Remember, you need to figure out how to get some antimatter, or some, well, not antimatter, sorry, dark matter, and then create the Alcuvian drive, warp drives, where you send a pulse, a laser beam in front, and then you shoot a laser beam behind at the same time. Um, you can fold space opposite to opposite to oh sorry, I shouldn't say opposite, but kind of like having a big giant mass. So if I had a big giant mass M, if I had a mass laser, this mass laser would fold the space-time fabric in front of my ship. So this is my starship. This is the Starship Nishank SS-101 or whatever it is. Right? So you shoot, and then you have to shoot the other way using some sort of repulsive gravitational mass and fold the space upwards. And so if you fold the space upwards behind you and then fold the space downwards in front of you, if you imagine this being like a tablecloth, here's my pi table, ha ha ha. If I pull on the tablecloth, yeah, we're reviewing. Look, we're doing dynamics. If you pull on the tablecloth with a force in front, while at the same time apply a force upwards, this is the repulsive gravitational force. Repulsive gravity. And so if you had a bubble or an object here, M, and you were sliding the tablecloth, you can see how you can force the object to move forward. Yeah, you can essentially travel faster than c. Now, the thing is, it feels like you're traveling faster than c, of course, but in reality, you're not traveling through space faster than c. You're just using space. Space is moving through you. Therefore, you're using space to circumvent this speed limitation. Right? Remember, nothing can travel faster than the speed of light through space, but if you can work around that limitation by folding space, then yeah, I suppose You can move from one part of the universe to the other at a smaller amount of time that it would require if had you move straight through space. And of course, the other way would be to circumvent space altogether and just funnel through from one part to the next through hyperspace. High school, I mean hyperspace. Um, easy, easy. Now this is the Einstein-Rosen bridge, or just create your own wormhole. If you're going to create a laser, might as well create one that's so powerful that it, instead of just folding the space, might as well poke a hole through space. You never know where you're going to end up or when you're going to end up. All right, back to the basics. Dynamics. Of course, all AP1 stuff, force, call. Actually, it was written as dpdt, right? It's just that most of the time my mass isn't changing, and therefore I can factor it out, and I get mdv/dt, and so that's where the amount comes from. But when mass is changing, then we have to account for that into dp instead of just dv. Sigma equations followed by systems. Recall that when you write sigma equations, the only time, let's see, here's like a wheel, and the rope is just wrapped around this wheel, no other object. So it could be you being lowered as this wheel turns clockwise. If m and b is changing, what we do chain rule? Yeah, derivative m times v plus derivative v times m, etc. You can take a look at the rocket equation. It should be in your chapter summaries. Now, if you have systems that are connected, we have to relate the accelerations together. Here's m1, here's m2, okay, and one way to do this is to remember one of them goes down, one of them is moving to the right, etc., and then change the ma at the end. So if I did sigma f for 1, I get tension up. Let's say ideal. We'll leave the non-ideal when we talk about moment of inertia during the rotational dynamics. Ft minus m2. So that means when we have an ideal pulley, the tensions on both sides are equal. Let's do very small friction, but not enough to slow stop the system from accelerating. Non-ideal will be done during rotational dynamics. So this is when we do the negative MA, because A represents the acceleration of the system, or in this case the acceleration of block M1A, and if I do sigma F2, we can see how the Oh, I put 2 here. This is supposed to be T. T. Tension 2 is pulling me to the tension on block 1. Ooh, man, so many mistakes today. This is FT1, this is 2, this is 1. All right. Tension is pulling me to the right minus the friction force. Mu K M1G. And it is equal to M1A. It is equal to M1A. Okay, so this is the only time we actually manually insert a negative sign in our equation. Otherwise, you leave the right side of the equation alone. The result of the tug of war between all of your forces will tell you what the A value is. So the only reason we put a negative sign is because when A is a positive number, it has to be negative for the other one. Now the workaround is to use a linear model. Instead of looking at it, oh there we go. Instead of looking at it with the horizontal and vertical axes, you can use the linear model, where in the linear model you have M1 being pulled to the right by the tension force. And then M2 is being pulled to the right by a force called gravity. Okay, so in this model, in this linear model, so just flatten it out. I was doing that before it got cool. What? What do you mean? You learned this last year in AP1. And in the flat model, you can see how M2G is to the right, tension is to the left on M2. So you, interesting. Well, I hope at least some of you remember us doing this last year. FT is pulling us to the left. And so M2G is, M2 is accelerating to the right in this linear model. So I'm going to keep it positive. Here we have friction. So tension minus the friction force is equal to M1A. So all the A's are now positive. Can we get a pull? Pull? P-O-L-L? I guess the only student I would think who would remember would be Jason. If Jason were here, he would remember. All right. Now the new stuff. So what was new this? Well, we had banked angles. That was definitely new. Banked angles, and this is something you need to know how to derive. Let's take a look at the cross section of a highway. It could be the highway exit ramp or something. Oh, this is very steep. Let's make it not as steep. There we go. Here's the angle. So this is a cross section, and this would be the back side of your car. So here are the wheels. So this is the back side. Here's your spoiler. That's a pi spoiler. This looks like similar to what we did, except we didn't have a loop thing. Loop thing? Yeah, we've done it. Oh no. So this is the back side of your car, and viewed from above, you're making a turn, a right turn. Right. Now the trick was to break down the normal force vector instead of the mg vector, because you're digging into the ground more due to the inertia of the object. What does a spoiler do? A spoiler gives you downforce, yes. So if you have a car, here's your DeLorean. If you have a car, you can see how all the air and stuff will flush into the bottom, and so if you go faster and faster, the air may kind of lift up your car, right? And so we want some F downwards. This will keep the car from flipping over if you go faster and faster. Right? Your spoiler is like a upside down airplane wing, basically. So it's the spoiler is an upside down airplane wing. And now if you flip your spoiler upside down, then you're gonna get lift instead of downforce, and so maybe you can start flying. Yeah, attach two spoilers upside down on the sides of your car, and see if you can fly. You know, you gotta shed some weight though, so get rid of all the leather seating and all that stuff. It's just a one seater. Uh, no carpeting, nothing. It has to be bare bones. All right. So anyway, the trick was to just to break down the fn vector instead of the mg vector like we normally do. Okay. Typically, the mg vector is greater than your normal force, but in this case, it is not. So as you make the round, you actually dig into the ground, so the ground has to push back even more. But so by breaking down the normal force, we get the y component of the normal force must equal to mg, and that equals 0. Oops. I should write it in sigma equation form. So sigma fy is equal to fn. Well, let's take a look at our angles here. This angle up top is theta, therefore this one here is 90 minus. Oh no, that doesn't look right. Oh well. The angle at the top is your theta, right? Control Z. Yeah, I don't think I have control. Oh well. So anyway, this is angle theta. We can say that fn cosine theta is equal to mg, or minus mg equals 0. In the x-axis, we have fn sine theta, and that's equal to, chat, what is it equal to in the x-axis? Hint, this is the helicopter view on the right here. Why 4? 4 equals r? What? Where'd you get 4 from? Yeah, it equals Mach, or mv squared over r. Hmm. Now let's do some follow up. Right, this was an ideal case where I don't have any kind of friction or anything, right? So no friction. This is the no friction model. Basically, if I angle the road correctly, I can safely navigate this turn without worrying about slipping off, even if my tires are bad. Okay, but what if as a physicist, of course, you want to maximize everything, right? What's the fastest you can go without killing yourself around this bend? That is the question. So, as a physicist, we want to maximize everything. Well, if I want to find the maximum, I'm going to need some help from for friction. Um, Now, when we're trying to go as fast as possible, right? Which way is the friction? Which way is the friction? Recall that friction always has to be the force of friction. Let's do some quick notes on friction. FF. There are two types. We have mu s. Actually, we learned mu r this year too, right? So mu s would be static. And then mu k of kinetic. Recall that the maximum static friction is equal to mu s Fn, right? Static friction is a dynamic force. It grows with the applied force. Grows with Fa until you break it, until you reach this maximum. And once you break this maximum, you now have kinetic friction, which is mu k, which is a static value. Right. And then we have mu r, rolling friction. The rolling friction was due to two things. What two things results in rolling friction? Chat. No, not not. See, remember, you got to be careful. This test is going to be more about explaining and less about calculating. So, what two physical elements or aspects of rolling on a floor results in rolling friction? Wow. Oh, God. We stumped the crowd. We stumped the crowd. I'll give you a hint. If you remember the rolling friction lab, we used some tablecloth or something like that, right? Why did we do that? The particles kind of break. Pressing down on the ground. Yeah. So either the ground kind of goes downwards. So if it was like carpet, if I zoom in, these fibers would squish down. Right. And the other element, the ground is not perfectly smooth, it's jagged and pressing down on it creates friction. Okay. Oh, that's what up. I see it. Never mind. So what else? So we got the ground covered. Hint, it's somewhere. It must be the other thing. So what about the wheel itself? I can cause mu r. Air? No, that would be drag force, not rolling friction, right? Rolling friction is not drag force. Drag force is drag force. Ground is we got the ground part, so everyone got the ground part. Check. So I need the other check mark somewhere here. All right. Well, uh, so if you take a look at your rubber tires, um, you'll see that it's not a perfect circle, right? Uh, yeah, the wheel isn't a rigid body. It actually squishes and turns more like a hamburger. This is exaggerated, of course, and due to the kind of like the weight of the entire car. So technically, it's on the axle. So the axle presses down on the wheel, which makes it kind of egg shaped or elliptical shape. Yeah. And so this constant changing shape and this going back and forth is also resulting in the rolling friction. Mm-hmm. All right, so we got mu s, we got mu k, we got mu r, and so when I am maximizing, and Nishank was alluding to something that is also important, and we'll talk more about it in rotational dynamics, and it's that the bottom of the wheel itself, when it's rolling, has velocity of zero, right? And due to that zero velocity, you get static friction instead of kinetic friction. Kinetic friction happens when you're skidding or when you're doing a burnout, whereas it rolls without slipping when you have nice static friction. All right, so if I want to maximize my speed, I need my friction to pull me back. Now, friction only acts parallel to the surface. That's kind of important to remember. Friction is parallel to the surface, so friction would pull me back downwards. Right? So imagine without friction, the car is going faster and faster. So the car would kind of go up the ramp as you're making this right turn. You'll go away from the center, right? You'll go away from the center if you go faster and faster. No, it's against the centripetal force. Um, there is a portion that goes into the ground which doesn't do anything. So we're only going to use the part that is parallel to the circle itself. Yeah. So only use the component that is parallel. All right. Uh, drag force. Let's talk about drag force. I suppose there could be drag. Drag force. The simple model was just gamma v. Technically negative. It's negative gamma v. Can someone tell me why it's negative gamma v? The simple, this simple model meaning. Yeah, v is a vector. This is a vector. Small mass, slow speeds. Yeah, so it's similar to other force equations, right? What other force equation is it similar to? And recall that complex model. Spring force, yes, spring force. So in the complex model we have absolute value of the drag force. Um, the 1/2 rho dA squared, or rho dA v squared, uh, is technically the magnitude because velocity is being squared and you're going to lose the direction. So you have to find it yourself. Hint, it opposes the way the object is moving. Now I'm using D. Some books use capital C sub capital D, coefficient of drag. Coefficient of drag. Right. So similar to spring force. Let's see, spring force. F is equal to negative kx. Okay, where F and x are our vectors. Okay, and so due to this model, Hookean springs, I'll use purple. What is Hookean? Well, it follows Hooke's law. And so it's nice and linear at 0 at 0. Right? Cool. All right, knowing this, I'm going to give you a question. This was actually on one of my honors physics labs. Ooh. So let's see if you guys can do it. All right. Y'all ready? Let me give you the scenario. I've done, yeah, of course. So here we go. Let's say we designed an experiment, right? So here's the story. We're designing an experiment to find K, the spring constant. And you should remember, hold your horses there, buddy. It's not that easy. So we want to find K, right? And I'm sure you've done many different types of experimental designs to find K of the spring constant. What can we say about the spring constant? Well, the spring constant. What can you say? Well, let's see. Give me everything you know about K. Is a constant. Well, excellent. Wow, good job. The spring constant is a constant. Anything else? Is a constant. It's constant. Poative. Newtons per. Yes, the units are of course newtons per meter. And if you knew the units, that kind of leads into how you could potentially, figure out how to get to it. It's some sort of force over some sort of distance. It's based on the material of the spring. Excellent, Ved. It depends on the build of the string. Yes. So not only is the type of metal or whatever you're using, but also the loops per length, kind of like an inductor, the loop density of the spring, the gauge. What is gauge? You might have heard this with the gauge of this wire or something like that. The radius. Close. You're close. Be more specific. All right, whatever. It's the thickness. So the gauge of the wire also matters. There you go. And so of course, so what kind of experiments can we do? So these honor students, okay. So when they did their experiment, they set up a ring stand, right? With a bunch of springs, okay, and then we put mg balance. Oh, right. So we put a little mass here, right? We put some sort of m, and we watch this m as it equilibrates. Ooh, that's a word that you should know. What is equilibrium? Or it's a great movie. You should put it on your summer watch list. When we reach equilibrium, the net force equals 0. So F net equals 0 at equilibrium, at EQ. So my two forces, my spring force and my gravitational force, cancel each other out, of course. Forwards and backwards reaction rates are equal. Yeah, they got it from force. Except KEQ, K-E-Q, is not KEQ in chemistry. KEQ is equivalent K. Just like KEQ. KEQ. Physics came first. So what do we do once we stretch it out? What do we do? They substitute. They don't borrow. What do we do? Well, we measure the delta, of course, and then we're done, right? What's next? Well, you can't just take one data point. You need more data. So now the next step is to change the mass, and then we'll get different stretches. Okay, so you start collecting data. You have these m's here, and these x's here, and you have data. What do you do with this data? What do you do what do you do? Here's some minor things that may mess you up. Graph what? The banana peel is right here. You got to be careful. What F? Yeah, it is true. F versus X. Well, what F? There you go, AP1 student. What you're graphing is the gravitational force, mg. And technically, if you want to find a positive value for your k, you'll have to accept the fact that all of your displacements are negative. So you might either just graph absolute values or absolute value of x's. You said what? Oh, well, okay. So you start graphing. When you start plotting these points, your graph is essentially a scatter plot. Right? All right. Then you do a trend line. Excellent. So you do a trend line, and then what do you do with the trend line? All right, hey, AP1 student, I'm using a ruler. +1. What do I do with the trend line? Those axes. Of course, this is in meters. And we want to use newtons for here. That is true. You don't get anything off. You just keep what you have. All right. Honors physics major. What do you do with this purple trend line? Slope. So you find the slope. Now, when you find the slope, make sure you don't use the data points. You want to use points from the trend line itself. So ideally, you want to capture everything, right? So pick a point that's here, and pick a point that's here, and then do the slope formula, and the slope will give you k. All right, now the actual question. So here's the actual question. After drawing the trend line, you notice that there is a non-zero y-intercept. Right? Yeah. So, in a paragraph length response, explain why we have this non-zero y-intercept, explain where it comes from, explain the model, explain any equation or any vocabulary terms that may be relevant in your explanation. So think about it. We technically did talk about this a little bit. Go ahead and answer in the comments below. Thanks for watching. I'll see you next time.